Hi, my name is Jake Muhlstein. I'm going to be presenting on lab number 7, counters. The lab objectives for this lab was to first become familiar with an important flip-flop application, or counters. 2, to be able to implement synchronous counters, or meaning that the states change on the clock's edge. 3, use logism to simulate those counters. And 4, learn about and use asynchronous control inputs on flip-flops, or inputs that change independent of the clock. The first counter that we were asked to create was a 3-bit globally synchronous up counter. That just means that we go ahead and count from 0 to 7 and loop. First, we find our transition table. Our expected output is just 1 bit greater than the current input. Once we find our transition, we fill out our transition table, we're able to find the min terms, filling out k-maps. And once we filled out our k-maps, we're able to find our reduced Boolean expression down below. And I've listed those down below. So for N2 we have A and B naught, or A and C naught, or B, C, and A naught. For N1 we have B and C naught, or C and B naught, and then for 0 we have C. We are also asked to implement this 3-bit counter with only NAND gates. NAND gates, once you've gone ahead and implement the NAND gates as seen on the left, we go ahead and reduce them to the minimum NAND gates needed. And then you can see here that I've implemented the input forming logic for each of the different gates using the reduced Boolean expressions from the previous slide. And once we start the clock input, see on the rising edge that each D flip-flop changes state compared using the next input that flows into the D flip-flop and then is outputted. And we see here it just cycles from 0 to 7 back down to 0. The second counter that we are asked to create was a 3-bit synchronous counter. We are asked to use the pattern of 1, 2, 4, back down to 1, 2, and so on. Again, we fill out our transition table. We only care about 3 of the numbers and their expected next states. The rest of them we fill out with don't cares. Once we filled out our transition table, we go ahead and we fill out our k-maps to find our reduced Boolean expressions. And in this 3-bit synchronous ring counter, we find that the reduced Boolean expressions are, because there's only one prime implicant for each of the k-maps, we are left with B, C, and A for the reduced Boolean expression. We also asked to use a reset on this ring counter. Reset it uses the sets and resets on the D flip-flops to go ahead and set set to the beginning value. So on Q2 and Q1 we have the reset, and then on Q0 we have the set, which sets it to 1. We can then see that it cycles 1, 2, 4, back to 1. 2, we go ahead and test the reset, bring it back to state 1, and then we use the clock input to go ahead and cycle back through. The next counter that we were asked to create was the glitch-proof gray counter. The gray code counter. We are also asked to use an increment input to determine whether or not the current state would transition to the next state. We fill out our transition table using the gray code count. And since there are only two bits for the current state, we only need 2 k-maps. And again, we are asked to use glitch proof, which means hazard free. So once we find our prime implicants in each of the k-maps, we add a redundant prime implicant, and this helps to eliminate false outputs. So here is the implemented logic of the transition table and the reduced Boolean expressions. We'll go ahead and cycle through here. You can see that the clock input where the increment is set to 0, it will not go to the next state. I'll go through each of the states to show that it does not increment. And then once we go back down to the first state, we'll go ahead and we'll keep the increment set to 1, and we'll see that the clock input functions as you would expect, going counting the gray code count. So in conclusion, what are some of the devices or places where counters are used and what insight was gained? Currently I am studying computer science. I'm taking CS 124 and counters are used all the time. We use it to cycle through information, perform certain logic functions. One of the examples would be to traverse an array of a string or of integers. And all that code is broken down eventually by the compiler to zeros and ones, and then it is used by the computer to go ahead and perform the logic. Thank you for listening to my presentation.